Hi everyone. I'm a PhD student from UC Berkeley, and also Berkeley Center for Responsible Decentralized Intelligence. Unfortunately, this topic would not be related to liquidity because I temporarily switched the title, and I thought this topic would be more interesting. So today I'm going to talk about towards secure, trust minimized, optimistic rollups. And this talk is based on a paper published in IEEE Security and Privacy 2024 named Specular. All right, so an overview of today's talk. So today's talk will be my talk will be have two sections. So first, I will talk about how do we reduce the trust assumptions and also enhance the security of optimistic rollups. And second, I also talk about how to do a trust and minimize smart contract for verification stack. So on the background, so why do we need optimistic rollup? Because Ethereum does not scale, so it has low throughput and also has higher fees. So we need to ask a question: how can we scale Ethereum throughput without compromising decentralization? So optimistic rollup is well-validated scaling solutions. So in case you do not know how optimistic rollup works, here is a quick recap. So in optimistic rollups, a user will send transactions to sequencer, which will put those transactions on chain. But unlike Ethereum, those transactions will not be executed on the Ethereum that is on chain. Instead, there will be an executor off-chain who will execute those transactions and generate the result, commitment of the result, and put it on chain. So if we are trusting the executor, then it will be fine. But an executor might be lying. So within a challenge window, we allow any challenger to submit a fraud proof to prove that the executor put the wrong result on chain to slash the executor and invalidate the result commitment. So in more than optimistic rollups, their objective is they want a low-cost normal execution, which means during the time when the commitment is not being challenged. And also, they want reasonably low-cost and bounded dispute resolution when there is a dispute and someone wants to submit a fraud proof. And thirdly, they want an identical developer experience to L1, and which often refers as the EVM equivalence. So both Arbitrum and Optimism, two biggest optimistic rollups, takes an approach called a compiled approach, in which they designed the fraud proof to be performing an interactive fraud proof over compiled L2 client binary, where the L2 client combines consensus layer client that is specific to L2, and an existing but modified Ethereum execution layer client implementation, for example, Geth or Nevermind. So in the compiled approach, how does this work? So first, they will compile a layer 2 client, for example, like the L2 Geth, to a lower level target VM. Like for example, for Arbitrum, it is Wasm, and for Optimism, it is MIPS. And they will use a vector commitment to commit to the resulting binary and put this commitment on chain in a fraud-proof module. And then when the fraud proof happens, they will enforce execution on binary at the target instruction level with the interactive fraud proof by looking up instructions against the binary. So this seems a little bit complicated, but we can get a key observation here is that the interactive fraud proof verifier is strongly coupled with the specific client binary, and which leads to several security and decentralization challenges. So overall, based on this observation, we can it leads to three problems. The first is it precludes the permissionless and trust minimized client diversity. And second, the TCB is too large to audit and infeasible to formally verify. And third, it causes governance burden on frequently triggered upgrade process. So let me get into these one by one. So the first problem is that this architecture does not allow the client diversity. and specifically the permissionless and trust minimized client diversity, and which leads to the conclusion that there's limited defense against monoculture failure because you can only use a specific client, and therefore a bug in this specific client can bring down the entire network and cause invalid state transitions. So why this happens? Because like the raw proof is running on a low-level VM, and this VM is a general VM. It's not just the EVM. So any program can be run on this VM. So you need this binary commitment to ensure it is running the correct EVM. And this binary commitment is permission, which means only the project owner can update this, and it is whitelisted. So only a certain type of EVM or the client can be used in the rollup. So what if we use a K-majority scheme? Like this does not help because it's not permissionless. So you need to make sure that K of n binary, it must be correct. And also, the validators must run all n clients to make sure they are able to challenge each other. Because like if you're only running one type of client, you cannot challenge with the validator who is running another type of client. And therefore, it does not scale. So increase number of clients whitelisted in this protocol, increase the component, affect the decentralization. So the second problem is that since the verifier is strongly coupled with the binary commitment, the entire L2 client software is in the trusted computing base. So the project must ensure that all the components in this trusted computing base are correct, including like you need to make sure the client software is correct. You need to make sure the WASM compiler is correct. You need to make sure like the prover is working, the vector commitment generator is working, and also the verifier is correct. So like the compiler is like a few thousand of code, lines of code, and also the L2 client software, which make it very hard to audit and even infeasible to formally verify. And the third problem is that since it is still, it is coupled with a specific commitment, therefore only a certain type of client can be run on the rollup. It's just not a type of VM, it's also a version of VM. Because like if you change the version of a VM, the binary will be different. Therefore, the commitment will also be different. So when you want to upgrade the version, you need to change the binary commitment, and which like you need to change the on-chain whitelist commitment. Then you must go through the governance. So even if GES does not like introduce any semantic changes like EIPs, but just like vulnerable patches or performance improvement, the client will change, which means the binary commitment will change. And in this case, it has to go through the governance to upgrade to a newer client. So how can we solve these three problems? So the observation is that the key to this problem is the strong coupled binary commitment. So we must decouple the protocol from the implementation. And to decouple them, the proof system must natively target high-level L2 semantics instead of lower-level VMs like WASM or MIPS. So, and includes both client consensus layer and execution layer client semantics. So in practice, like we designed an EVM native interactive fraud proof that we construct the one-step proof directly over the EVM instruction level instead of the lower-level VM instruction level. And in this case, it solved all three problems. Why? For the first problem, like this architecture allows intrinsic client diversity because any clients implement the same EVM. So they implement the same semantics. So any client can be used to participate permissionlessly in dispute resolution because they are all transactions on the rollup are on every client are having the same EVM execution trace. So we only need one client to be correct to make sure the fraud proof is correct. So we have intrinsic client diversity. And also since like we can use different types of clients to dispute with each other, the one validator only needs to run the client they trust to participate in the challenge game to secure the optimistic rollup, instead of like the previous solution. The validator needs to run n types of clients to make sure the rollup is secure. And it also has a minimal and trustworthy TCB, trusted computing base, and because like those clients are not in the trusted computing base anymore. Why? Because there's no binary commitment in the verifier. So the TCB of this protocol only includes the interactive fraud-proof verifier. And smaller TCB improves auditability. And since the verifier are enforcing the EVM semantics, it is possible to formally verify this verifier against existing EVM formal specifications. And third, it has it does not need to do frequent on-chain upgrades. Like because the verifier is enforcing an EVM semantics, only when the semantics change will this verifier be updated. So if you are just shipping a vulnerability patch or a performance improvement without affecting the semantics, you don't need to go through the on-chain governance protocol to upgrade your client in the rollup to participate in the rollup. Therefore, they can be directly shipped off-chain. Therefore, it is practical in this protocol to forfeit the upgrade keys. So maybe one day using this protocol, you don't need to have a contract proxy to guard the rollup contracts. So and it will become truly permissionless. So a little bit about how the interactive fraud proof verifier is implemented. So basically, we use a data structure that we can verify the initial agreed EVM state provided by the prover. And on-chain, we will simulate a single EVM instruction execution and verify the final state to match to assert if the simulated final state matches the prover's asserted state. So Specular is an optimistic rollup equipped with this EVM native interactive fraud-proof verifier, which provides three benefits like the intrinsic client diversity, the minimal TCB, and the infrequent on-chain upgrade. So in current implementation, it supports all the semantics defined by Ethereum spec and only modify the client minimally. So a little bit more on the design philosophy. So this protocol advocates two philosophy within it. First is trust minimization, that a bug or exploit in one client software stack should have negligible impact on the system's overall security. And the security of an optimistic rollup should therefore only depend on the conformance of a single software stack to the L2 protocol specification. So we're not relying on guess to be bug-free. And also advocates credible neutrality that only enforce minimal constraint over L2's execution semantics beyond as necessary to guarantee the security. So we don't need to modify Ethereum a lot to support rollups. And also, a validator should be able to operate permissionlessly using any client software stack they want, existing or new, without having someone's approval. All right, so this is a summary of this protocol. So Specular has minimal client modification, minimal TCB, intrinsic client diversity, and infrequent L1 upgrade. So to make this protocol even more secure or trust minimized, we can use the formal verification, as I talked before, to verify the TCB, that is the interactive foolproof verifier. So we can extract the semantics from the on-chain EVM simulator and verify against existing formal specifications. And now, in parallel, we also want to ask the question is, how can we further reduce the trust on the formal verification stack? So this is ongoing work, and some results are maybe preliminary, but I'm very excited to share this project towards a trust-minimized smart contract or formal verification stack. So what is the problem? The problem is that, as we know, on EVM, we're running EVM bytecodes. We're not directly running the Solidity program. So in this case, we have two verification targets. We can choose to either verify to do formal verification on Solidity or U, or we can choose to verify directly on the EVM bytecode. So if we are directly verifying, on Solidity, it is easy to write specification because Solidity or U is a high-level language. It has variables, it has functions, but we are trusting the compiler to make sure it is correct, besides the guarantee provided by the formal verification. Because if there's a bug in the compiler, you're just verifying the high-level code. The low-level code can still be buggy. But if you are verifying on the low-level code, it does not rely on the compiler anymore, but it is very hard to write the specification. So can we create a verification stack that is first, friendly to write specification, and second, not having the compiler in the TCB? So this is the outline of our approach. So basically, we do both. So we verify on the high level, and we verify on the low level. But instead of writing specification on the low level, we are trying to prove the refinement between the formal model of the high-level language and the formal model of the low-level language. So if you are proving they are the equivalent, we only need to verify it on the high level, and we get the same guarantee on the low-level code. So on the low-level code, which is EVM bytecode verification, the approach is simple. We translate the EVM bytecode into Daphne program into EVM by Daphne by first building the control flow graph of the bytecode program. And for each basic block, we use EVM Daphne to generate the program condition. And we use a symbolic execution-like verification approach, which compose those basic block conditions with branching conditions to represent the program. And for external control calls, we use an approach we call level condition, that we treat calls as an uninterpreted condition at first, and we generate possible conditions of possible call contract, and we insert them back and to create the condition of the entire contract. So as an example, in the comment, those are the bytecode that yet to be verified. And the EVM Daphne translator will translate those EVM bytecode into a Daphne program like this. And on the UL side, we can translate UL program to Daphne using UL Daphne by first using the Solidity compiler to generate UL AST from UL program, and then compile UL AST to UL Daphne. And this is an example of compiling the UL program into UL Daphne program. And we can do the refinement by if we want to do the refinement on the semantic equivalence. That is we are making sure the two programs are identical. We only need to compare the two formal models. But this is very hard, so maybe we can do something simpler. That is, we want to enforce specification equivalence, that both bytecode program and UL program follow the same specification. So how can we do this? So the key problem is the variable and function mapping between UL and bytecode is missing. So maybe you can do a certified compiler that we formally model the compiler, and so we can create this abstract compiler to calculate the mapping. And maybe another approach is more interesting, is that we can do some instrumentation to augment your protocol and let the compiler to output those mappings. So I'll skip this part because the time is over. But this concludes my talk today. So on the left-hand side, we want to do the trust minimized optimistic rollup, and on the right-hand side, we want to do the trust minimized from a verification stack. Yeah, thanks everyone.